So this example didn't get finished, so I'm going to go ahead and finish this example. I'll start it from the beginning. This one is where we're going to solve the differential equation for y prime plus y equals 0. One of the things to remember when we solve these is that this one actually does have constant coefficients. So we could do this one another way. I just want to show an easier way to solve it first. But we usually solve these when we don't have constant coefficients. So I wanted to show you how we do these. We are going to assume that y is equal to the summation n equals 0 to infinity of c sum n x to the n. So we're going to assume that that is the solution, which means we can plug it in and show that one side equals the other. So we can see that it works that way. We can plug it in. Of course, to plug it in, that means I need to know what y is, which we know. I also need to know what y prime is. So we need to first find what y prime is. Well, when you take a derivative of this, you're taking a derivative of each individual piece, each term by term. That will always get you, bring the power down, and then subtract 1 from the power. And so this would be the summation n equals But now let's see where we start. So remember, this is actually C0 x to the 0 plus C1 x to the 1 plus C2 x to the 2 and so forth. The derivative of that first term is 0. The derivative of C0 is 0. It's just a constant. So we're not going to start. We're going to have 0 plus C1 x, C1 plus C2 x plus and so forth all the way up. So this first term actually is gone. So we don't start at n equals 0 anymore. We actually start at n equals 1 to infinity. All right, so this is actually what the derivative is. Now we can plug it in. So we've got 4 times that derivative. Plus the original y, which is n equals 0 to infinity of cn x to the n equals 0. So great. So now what we want to do is we want to actually try to find a way to combine these to be 1x, so we can factor that x out and find out what those constants are. That's the whole idea. We want to find out what those coefficients are. So one of the things I need to realize is that I want these both to be x to the n. This one's x to the n minus 1. So what we need to do is we need to do where we're shifting it. We're not shifting necessarily the index per se. We're not trying to make them both start at n equals 0. We're trying to get them both to be x to the n. So in this case, we need to let n equal n plus 1, because n plus 1 minus 1 will give me x to the n. So we want it to be n plus 1 in this case. In this case, we already have x to the n. So we don't need to do anything to the summation n equals 0 to infinity cn x to the n. We just need to do it to the very first term, the summation n equals 1 to infinity n cn x to the n minus 1. So we've got the 4 out here. We have the summation. We're not going to have n there. We're going to replace it n with n minus 1. Or n plus 1, sorry. And then we're going to go from n plus 1 equals 1 to infinity. Instead of having n here, we're going to plug in what we think n is equal to. N is equal to n plus 1. And then we're going to have c sub n plus 1. And then we're going to have x to the n plus 1 minus 1. Then the other one, again, nothing changed with that one. So we're just going to write the summation n equals 0 to infinity of cn x to the n equals 0. All right, so now when I do this, I can start simplifying this a little bit. We've got 4 summation n plus 1 equals 1 means n is going to equal 0, solving for n. So n equals 0 to infinity. N plus 1, c sub n plus 1, x to the n. Plus the summation n equals 0 to infinity of c sub n x to the n, and this whole thing equals 0. Great. So now what we're going to do is we're going to try to put these together into one summation and factor out the x to the n. Notice both of these have an x to the n, so we can actually put them together and factor that out. We also notice in this case, both of them are the summation n equals 0 to infinity. So we can put these into one summation. I'm going to bring that 4 inside the first summation. So n equals 0 to infinity. Since they both start there, we can just put them together. This will be 4 times n plus 1, c to the n plus 1. We're going to factor that x to the n out, so I'm going to leave it out for the moment, plus the c sub n, and we factor out the x to the n equals 0. Again, our whole process of what we're going to do here is we're trying to find out what these coefficients are. The only way this can actually equal 0 is either if x equals 0, which is kind of boring, or if these coefficients are equal to 0. So the only way we can actually get 0 out of this is if these coefficients are equal to 0. So what we're going to do is we're going to look to see what are those coefficients. So we have 4 times n plus 1 times c sub n plus 1 plus c sub n equals 0. So what we could do here is we could actually solve for one of these two c's. It makes more sense to solve for the c, the n plus 1, because it's just one more n, so it's a little bit easier to solve for that one. We're going to get the c to the n plus 1 by itself. So it's going to give me a negative cn over 4 times n plus 1. The thing to realize is going back to my summation started at n equals 0 and goes on to infinity. So I need to remember in this case, because my summation started at n equals 0, my n starts at 0, goes to 1, 2, and so forth forever. So let's actually try some of those. Let's actually see if we can just see what pattern we're getting here. N equals 0 means that we're going to have c sub 0 plus 1, which is c sub 1. It's going to be minus c sub 0 over 4 times 1, because 0 plus 1, of course, is 1. And so we end up with it's equal to minus c sub 0 over 4. If we know what c sub 0 is, we can actually find out what this is equal to. Sorry about this. If we know what c sub 0 is equal to, then we can find out what c sub 1 is. Great. Let's go ahead and keep going. Let's try n equals 1. That means we're going to have c sub 2, because n is now 1, so we have 1 plus 1 is 2, minus c sub 1 over 4 times 1 plus 1 is 2, so 4 times 2. Cool. Wonderful. One of the things I notice here is if I know c sub 1, I can find c sub 2, but I do know c sub 1. C sub 1 is minus c0 times over 4. So I could actually say that c sub 1 is c0 over 4 times 4 times 2. Well, that's minus, oh, wait, we have another minus. So we actually now get positive. So there's no longer minuses because we forgot that minus, minus a minus. So we actually, if we can give you C0, we can also find C sub 2. And in fact, 4 times 4 is 4 squared. So it's 4 squared times 2. I'm not going to find out what this is equal to because I'm looking for patterns. So if I try to find out what this is, I've lost my ability to look for patterns. Let's try n equal 2. That would be C sub 3, because 2 plus 1, of course, is 3, minus C sub 2 over top of 4 times 2 plus 1 is 3, so 4 times 3. Well, again, if I know what C sub 2 is, I can find C sub 3, but I do know what C sub 2 is. C sub 2 is C0 over 4 squared times 2. So it's going to be minus C sub 0. 4 squared, there's another 4, so we're going to get 4 cubed times 3 times 2. So again, if I know what C0 is, I can find C1, C2, and now I can find C3. So all I need to know is what that C0 is. Let's do a couple more. Let's do n equals 3. That would be C sub 4. That'd be minus C sub 3 over 4 times, well, 3 times 3 plus 1 is 4, so 4 times 4. Again, if I know C sub 3, I can find C sub 4, but I do know C sub 3. It's minus C0. Minus and minus gives me positive C0. 4 cubed times 4 times 4. I could do this as 4 to the 5th. Instead, I'm going to do it as 4 to the 4th times 4 times 3 times 2. You'll see in a moment why I'm starting to see a pattern, so I kind of wanted to keep it that way. So that's why I wanted that 4 times 3 times 2. And then I notice that we have this now. Let's do one more and see if we can see a pattern. N equal 4 means we're getting C sub 5. That'll be minus C sub 4. Make sure that looks like a 4. Sorry about that. And then we're going to have 4 times 4 plus 1 is 5. So 4 times 5. Again, if I know C4, I can find C5, but I do know C4. It is C0 over 4 to the 4th, but then another 4, so it's 4 to the 5th times 5 times 4 times 3 times 2. I could keep going with this, but let's see if we can come up with a pattern. One thing I noticed is I have 4 to the 5th power. My n was 4. This is the n plus 1. So notice my C sub 5 has a 5. My C sub 4 has a 4. My C sub 3 has a 3. My C sub 2 has a 2. My C sub 1 also has a 1. So we do see kind of that pattern. So if we think about what C sub n is equal to, that would equal 4 to the n, because we see that 4, 5, and that 5 there. We know we have a C0. Let's see if we get another little pattern. Then you don't always have to find patterns, but sometimes it's nice to find them. One of the other patterns I noticed, we start with a negative. We went positive, we went negative, we went positive, we went negative. The C1 is negative, the C2 is positive, 3 is negative, 4 is positive, 5 is negative. So always to the, when we're an odd number, we're going to have a negative. So that would tell me that there's going to be a negative 1 to the nth power. Cool. That's great too. And then when the last thing I want to do is I notice I have 5 times 4 times 3 times 2. I have 4 times 3 times 2. I have 3 times 2. I have just 2. And I have just 1. If you think about it, this is actually times 1. And in fact, all these have a times 1. So I could put a times 1 in all these. So we actually have 5 times 4 times 3 times 2 times 1, 4 times 3 times 2 times 1, 3 times 2 times 1, 2 times 1, and just 1. Notice, again, my n is 1, 2, 3, 4, 5. Ignore these n's here. We're trying to come up with a different n here. This number here, 5, this is 5 factorial. This is 4 factorial. This is 3 factorial. So this would be n factorial. So we now can find out what y is. You can do y 2 different ways. You can do y is just saying it's C0 plus C1 times x plus C2 times x squared plus C3 times x cubed plus C4 times x to the 4th plus C5 times x to the 5th, and just keeps going like that forever and ever and ever. So plus, plus, plus. We now know, we don't know what C0 is. We can just leave it as C0, but we do know what C1 is. C1 was negative C0 over 1 factorial times 4 to, there is no 4, so it must be 4 to the 0. X to the, wait, sorry, there was a 4 in that first one. There is a 4 and it is to the first power. So we have a C, a 4 to the 1. Then we're going to have plus C2 was C0 over 2 factorial times 4 squared plus C3 was negative C0, so it's not plus anymore, it's minus. Minus C0 over 3 factorial, 4 to the 3, all times x cubed. Forgot my x squared here. Plus C4 was plus C0 over 4 factorial, 4 to the 4th. That would be x to the 4th minus C0, 5 factorial, 4 to the 5th, x to the 5th, plus dot, 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 forever and ever and ever. And if you want, you can also write it with that notation we just found. So we could actually write this. Notice all of these have a C0 in them, so you could factor that C0 out. And then the rest of them will be the summation n equals 0 to infinity of -1 to the n. C sub 0 is gone, so we don't need to worry about the C sub 0 anymore because we factored it out. Over 4 to the n times n factorial x to the n. So it's another way to write it. And that's how we can solve this. So this is what this would be. If you want, you can try to see if this is actually one of the known functions, and you can find out what that solution is from that, or you can just leave the answer like